In this video, we're going to go over the KutaSoftware Infinite Pre-Calculus Free Worksheet Extrema, Increase, and Decrease. And before we jump into this worksheet, if you haven't already, don't forget to subscribe to my channel. Now for numbers 1 and 2, we're going to approximate the relative extrema of the function. Now relative extrema will either have a relative maximum or a relative minimum. A relative maximum is an extrema that's higher than any of the points nearby. A relative minimum is an extrema that's lower than the points nearby. So looking at number 1, we can see that we have two extrema. We have an extrema at the point -3, -1, and we have an extrema at the point 1, -4, because each of those points is either higher than the points nearby or lower than any of the other points nearby. Because if you notice, this graph increases to a certain point, and then at that point it begins to decrease, and then it decreases till a certain point, and then at that point it begins to increase. And what I mean by increase and decrease is that x values get larger, the y values in turn also get larger, that's increasing, or as the x values get larger, the y values will get smaller or decrease. So that's when the function is decreasing. And just a side note, so when you get into the more advanced sections of calculus, the extrema are when the derivative equals 0, and a function is increasing if the derivative is greater than 0, and you can know that a function is decreasing if the derivative is less than 0. So just keep that in mind for a later lesson. But for now, we have -3 and -1 as one extrema, and that is higher than any of the points nearby. So it is a relative maximum. And that's at the point -3, -1, and then 1, -4 is lower on the graph than any of the points nearby. Therefore, it is a relative minimum. So again, -3, -1 is a relative maximum, and 1, -4 is a relative minimum. Now let's go on to number 2. And number 2, again we can see two extrema. We have an extrema at -2, that'll be -2, +2, and an extrema at 0. And that's 0, 0. So -2, 2, and 0, 0. And that's because the function is decreasing until it hits that point -2, 2, and then it begins to increase again. So -2, 2 is the lowest point in its area. So that is a relative minimum. And 0, 0, we can see that the function is increasing until it hits that point 0, 0, and then it begins to decrease. So 0, 0 is the highest point in its region or in its area. Therefore, 0, 0 is a relative maximum. And that just goes to show you that you can have a relative minimum that is essentially higher up on the graph than your relative maximum, because it's all dependent on the points of the function that are nearby. So remembering that, let's continue on to 3 and 4. And numbers 3 and 4 were to use a graphing calculator to approximate the relative extrema of each function. So let's go ahead and enter this in on a calculator. So in number 3, we have the function y equals -x cubed plus 4x squared minus 4. And looking at this graph, you can see that we have two extrema. One occurs at the point 0, -4, and the other occurs at the point, let's approximate to 2.7 and 5.5. And looking at the graph, 0, -4 is a relative minimum because the function decreases until it hits that point, and then it turns and starts to increase again. So that is the minimum, and then the relative maximum is 2.7, 5.5, because the function is increasing to a certain height, and then it changes and starts to decrease. So again, for number 3, we have a relative minimum of 0, -4, and a relative maximum of 2.7, 5.5. Let's continue on to number 4. And number 4, we're looking at the function y equals x squared over 4x plus 4. So we have that y equals x squared over 4x plus 4. And looking at this graph, we're going to have one relative maximum and one relative minimum. And if you remember from our previous worksheet, we'll have a point of discontinuity at x equals -1. Our relative maximum, looking at the function on the left-hand side, it's increasing till it reaches a certain point, and then the values begin to decrease. And that point is -2, -1. So that's a relative maximum. And again, that was at -2, -1. And looking at that next point, our function is decreasing, decreasing, decreasing until it hits 0, 0, and then it begins to increase. Therefore, we have a relative minimum at 0, 0. And that's our solution in number 4. Now let's move on to numbers 5 and 6. In numbers 5 and 6, we're given the graph of a function, and it says to approximate the intervals where each function is increasing and decreasing. So let's start by looking at number 5. Now remember, a function is increasing or decreasing until an extrema, or a point of discontinuity. But because number 5 is continuous, we know that it's going to be switching, either increasing or decreasing at those extrema. So let's locate those. Our first extrema we can see is at -4, -2. So that occurs when x is equal to -4, and then our function begins increasing until we hit x equals +4, and then it begins decreasing. So when we're writing our intervals, we're going to be using the domain. That is why I only wrote down the x values at which our extrema occur. So you can see, starting off, the graph is decreasing. So we're going from -infinity, and it's decreasing until that point where x equals -4. So from -infinity to -4, that interval, our function is decreasing. Then, from x equals -4 to x equals 4, our function is increasing. So increasing over the interval -4 to +4, and then once it reaches +4, it begins decreasing again. So from +4 to +infinity, we have another interval of decrease. So it's increasing over the interval -4 to 4, and it's decreasing over the interval -infinity to -4, and 4 to +infinity. Now let's look at number 6. Let's first locate the extrema. We have an extrema where x equals -1, an extrema at x equals 0, and an extrema at x equals +1. So we have two relative minimums and a relative maximum. So to start off, our function is decreasing. So using our domain for our interval, so our x values, we're going from -infinity, and the function continues to decrease until that point where x is equal to 1. From there, our function begins to increase, and it increases until that next relative extrema, the relative max, at x equals 0. So it's increasing from -1 to 0. Then, after that, it begins decreasing again until that next relative extrema. So it's decreasing from 0 to 1, and then finally it's increasing again from 1 to +infinity. So it's increasing over the intervals -1 to 0, and then 1 to infinity, and it's decreasing over the interval -infinity to 1, and then 0 to 1. Let's continue on to our next section. Our next section, we're going to do the same as in numbers 5 and 6, except now we're going to be using a graphing calculator given the function, but we're still finding those intervals where the function increases and decreases. So writing our first function, we have x to the fourth minus 2x squared minus 3. And with our graphing calculator, the relative extrema are normally pointed out to us. So we have one relative extrema at -1, -4. So when x equals -1, we have a relative max when x equals 0, and then a relative min when x equals 1. So -1, 0, and +1 are our x values for our extrema. And to start off, the function is decreasing. So it's decreasing, going from -infinity in the x to -1 in the x. So again, that's -infinity in the x to -1 for x. After that, it begins increasing, and it increases until that next extrema. So from -1 to 0. Then it begins decreasing again from 0 to the next extrema, 1. And then after that extrema, it increases as x approaches positive infinity. So then another increase from 1 to infinity. And that's our solution in number 7. Now in number 8, our function is the opposite, or negative, 2 over x squared minus 1. And looking at this function, we have one extrema at 0, 2. And we have 2 points of discontinuity. The points of discontinuity occur at -1 and +1, and a relative extrema, which is the minimum, occurs at x equals 0. If you look, our function is decreasing until that point of discontinuity at x equals -1. So our function is decreasing from -infinity until that point of discontinuity to -1. After that, we can see that from that point of discontinuity, -1, our function is still decreasing, and it decreases until that relative extrema at 0. So our next decrease is from -1 to 0. And then from 0, we're increasing until that point of discontinuity, which is x equals 1. So we're increasing from 0 to 1. And then, again, our function is still increasing. So after that point of discontinuity, until infinity, our function is increasing. So from 1 to infinity, our function is increasing. But it is important to separate those intervals because the function was not continuous throughout. It had 2 points of discontinuity. So even though as we increase our x values, after the first point of discontinuity, the graph continued to decrease, and after the second point of discontinuity, the graph continued to increase, because it was not continuous, we needed to make that clear on the intervals. Now let's move on to the second page. For numbers 9 and 10, it says to approximate the relative and absolute extrema of each function. Then approximate the intervals where each function is increasing and decreasing. So the new term that's introduced here is absolute. So let's go ahead and locate our relative extrema at the start. We have one relative extrema that occurs when x is equal to 0, because the graph continues to decrease, so we do not have a relative extrema on this side, but in the middle we have a relative extrema, and then the graph continues to increase, so again there's no relative extrema on this right hand side. Now we can see that it occurs when x is equal to 0, but we need to solve for that y value. So we'll plug 0 in for x. That means that y is going to equal -3 over 0 squared minus 4. So that's going to be -3 over -4, which will be a positive 3/4, which in decimal form is 0.75. So our relative extrema, which is a relative minimum, because it decreases until it hits that point and then it begins to increase, so it is the lowest point in its region, occurs at 0, and on our answer key, they rounded to 0.8 for the y value. So you can either round up to the nearest tenth or leave it at 0.75. I'll go ahead and round up just so that it matches that answer key. Now our next step was to write down the absolute extrema. However, there is no absolute extrema, so we only have a relative minimum. There is no relative max, so there's no relative maxima, and there's also no absolute extrema. And that's because even though we have a relative minimum of 0 and 0.8, it is not the lowest point because the function continues on with y values approaching negative infinity. Therefore, there's no absolute extrema. So again, just to reiterate, a relative min or a relative max is the lowest or greatest in their area or in their neighborhood, but an absolute is the greatest or lowest point across the entire domain. So because this function goes up to positive infinity in the y value and it goes down to negative infinity in the y value, there's no absolute. And then our last step was to approximate the interval where the function is increasing and decreasing. So the function is increasing from that relative minimum of 0 to that point of discontinuity 2, and then from that point of discontinuity, the function is still increasing all the way to infinity. Now the areas where the function is decreasing, that's from negative infinity to the first point of discontinuity at negative 2, and then from that point of discontinuity to the relative min. So from negative 2 to 0. And that's our solution for number 9. Let's move on to number 10. In number 10, we have 2 points of extrema. We have a maximum that occurs at x equals 0 and a relative minimum that occurs at x equals 2. And when x is equal to 0, y is equal to negative 3, and when x equals 2, that y value of the function is negative 7. So we have a relative min at 2, negative 7. We have a relative maximum at 0, negative 3. And again, we have no absolute. And that's because the function continues to positive infinity in the y and to negative infinity in the y. Now we see where the graph is either increasing or decreasing. The function starts off increasing from negative infinity all the way to x equals 0. That function is increasing. Then the function takes a turn and begins to decrease from the relative max to the relative min. So from 0 to 2, that function is decreasing. And then lastly, the function increases from that relative min of 2 all the way to infinity. And that is our solution in number 10. Moving on to number 11, we do not have a relative minimum, but we have a relative maximum, and that occurs at the point 3, 5. But it is not just the relative maximum, it's actually the absolute maximum because that is the greatest y value in the entire graph. So we have no absolute or relative minimum, but we have an absolute maximum, which it's safe to assume is also the relative maximum, at 3, 5. Now we're going to see where the function is increasing and decreasing. And because it's just a parabola, it's increasing from one point until that max. And because the parabola opens down, it's increasing until that maximum. So it increases from negative infinity all the way until the x value for the maximum, which is 3, and it's decreasing from that maximum x value to positive infinity. So from 3 to infinity. And that's our solution in number 11. Lastly, for this set of directions, we're going to go over number 12. In number 12, let's find our max and min. One max occurs at -5 for x, and the other occurs at +5 for x. And if that's difficult to see visually, feel free to graph this on a graphing calculator and zoom in to see that it is indeed -5 and 5. However, in order to solve for the y value, let's plug each of those in. So I'm going to start by plugging in -5 for x. Our function is the opposite of 25 times x, so 25 times -5, over x squared, so that's going to be -5 squared plus 25. 25 times -5 is -125, so we have the opposite of -125 over -5 squared is 25, and 25 plus 25 is 50. So the opposite of -125 over 50 is the opposite of -2.5, which is a +2.5. So when x is equal to -5, y is a +2.5. And then solving for when x is +5, I'm going to have the opposite of 25 times 5 all over 5 squared plus 25, which will give me -125 over 50, and that's equal to a -2.5. So when x is +5, y is -2.5. Now at -5, 2.5, that is the highest point in the entire graph. So that's going to be an absolute maximum. And at 5, -2.5, that is the lowest point on the entire graph, so that's an absolute minimum. So again, because this was a relative maximum and the highest relative max, -5, 2.5 is the absolute max, and because this was the relative min and the lowest relative min, then it's the absolute minimum, 5, -2.5. Now we're going to see when that function is increasing and when it's decreasing. Starting off, we're increasing from -infinity until that absolute max at -5. So we're increasing from -infinity to -5, and then we decrease from -5 to +5. And then from there, we're increasing again from 5 to infinity. And that's our solution in number 12. Now onto the critical thinking questions. For number 13, it says to write a function that has the following relative maximums. That's 1, 1, 2, 2, and 3, 3. And this seems rather difficult, but we just have to remember a couple things from Algebra 2. If you remember Vertex form of a parabola, we have the function f of x, and that's going to equal a value a times x minus h squared plus k. Now this form, h and k, that's the vertex of the parabola. However, we have to have 3 different maximums, and this works because h and k are equivalent for each. So we'll have x minus 1 squared, we'll have an x minus 2 squared, those will get multiplied, and then we'll have x minus 3 squared, and we're going to need to add that to our k value, but remember, h is equal to k, so that's going to be the x values that we plug in, so plus x. So we can see that if we were to plug in a 1, 1 minus 1 is 0, and 0 times any quantity is 0, but we're adding 1. So plugging in 1 for x, we'll get 1 for y. Now let's say we plug in a 2. Plugging in 2 for x, 2 minus 2, that's going to be 0 squared, which is 0. So this quantity will equal 0, but we're plugging in 2 for x. So that's going to be a positive 2. And then again, if we plug in 3 for x, 3 minus 3 is 0, and any number times 0 is 0, but remember we're plugging in 3 for x, so 0 plus 3 is equal to 3. So we'll get 3 for our function. However, writing it this way, they're not necessarily relative maximums. We need a value that's negative, and in order to see the curve and double check with our graph, we'll make this number larger. So let's make it negative 10 so we get those distinct curves for our graph. So if we have y equal to negative 10 times x minus 1 squared times x minus 2 squared times x minus 3 squared plus x, when we plug in 1 for x, we will get 1 for y. If we plug in 2 for x, we'll get 2 for y. And if we plug in 3 for x, we'll get 3 for y, because plugging in a 1, 2, or 3, the multiplication of our first term will be 0. So we'll either have 1, 2, or 3. And I graphed this out on a graphing calculator so that you could see. Negative 10 times x minus 1 squared times x minus 2 squared times x minus 3 squared plus x. We could have also used another number such as negative 20. But this coefficient has to be larger in order to get those as a maximum. You could even use negative 100 as the coefficient. But remember, the coefficient has to be large enough to make sure that that is indeed the relative max. So for example, using something such as negative 1, it does not decrease to give you those 3 distinct relative maximums. So you need to do a smaller number such as negative 10, negative 20, negative 30, and so on. Now on to number 14. It asks, is it possible for a continuous function to have only the following extrema? And that's only the following extrema. So 1, 1, 2, 2, and 3, 3, where 1 and 3 are maximums and 2, 2 is a minimum. So if we were to look at this visually, if 1, 1 is a max, that means it has to begin to decrease, but in order to get a relative min of 2, we need to increase enough so that we're decreasing down to 2 so that we can turn and increase again. However, that means that we're going to need to have added another relative min and another relative max. So that is not possible for a continuous function. We could attempt this not using a continuous function and then having a jump. However, it says that the function needs to be continuous. Therefore, it is not possible. And again, that's no, because the function can't be decreasing to the right of x equals 1 and decreasing to the left of x equals 2, yet jump from y equals 1 to y equals 2 with no periods of increase without it being discontinuous, so without it being not continuous. There would need to be some other relative min or max, but it says it can only have the following extrema. Therefore, it's not possible. And that wraps up the pre-calculus free KutaSoftware website worksheet on extrema, increase, and decrease. If you have any questions, please leave them in the comments below. And before moving on to a different video, remember to like, subscribe, and share. All likes and subscriptions are greatly appreciated.